Here are some ACS Gen Chem 2 practice problems. We're dealing with dynamics. A catalyst increases the rate of a reaction by A. Changing the mechanism of the reaction, B. Increasing the activation energy of the reaction, C. Increasing the concentration of one or more of the products, or D. Decreasing the difference in relative energy of the reactants and products. So I think this is true, but we'll keep looking at the others. When we see this word mechanism, we need to realize that that means that is a reaction pathway from start to end, to finish, start to finish. It's very messy. And a catalyst speeds up a reaction and it lowers the activation energy. So this could very much be true because we are changing the mechanism of reaction then. B, increasing the activation energy. See, that's the opposite of what I just said, so that's not it. A catalyst lowers activation energy for reaction. If you remember, this is the activation energy right here of a reaction, and a catalyst will make that smaller. Increasing the concentration of one or more of the products. No, a catalyst doesn't deal with the concentration. Decreasing the difference in relative energy of the reactants and products. I don't know what that's talking about. That's not it. This is our answer. Next question, consider the reaction. The rate equation for this reaction is, which of these mechanisms is or are consistent with the rate equation? So our rate equation here, the slow step, something we need to know. The slow step is the rate determining step. Rate determining step. I spelled everything wrong. I'm trying not to wiggle this. So these are the steps we're going to be caring about. This one, Cl2 and H2S is consistent with our rate, so that should be clear here. For the second mechanism, our slow step has Cl2 plus HS minus, which cancels out because it is produced and then used. And then we're just left with Cl2, which is not consistent with our rate law. So 2 is incorrect, so anything with 2 is going to be wrong. We already saw that 1 is correct, so it's not D, so A is our answer because the slow step, the reactants match up with our rate law. 22. A certain reaction has a delta H of negative 75 kilojoules and an activation energy of 40 kilojoules. A catalyst is found that lowers the activation energy of the forward reaction by 15 kilojoules. What is the activation energy of the reverse reaction in the presence of the same catalyst? So we can write out our reaction coordinate graph and say, okay, that was very small, I should have written it bigger. Originally we have 40 kilojoules for activation energy, and our delta H is negative 75. But then our activation energy is lowered by 15, so it becomes 25. So you can write another one. Oh, I just kind of made it. This isn't to scale. 75. And so what we're looking for is the activation energy of the reverse reaction. This is the activation energy of the forward reaction, but the reverse reaction is going from the products to the top of that bump right there, and that is our activation energy of the reverse reaction. So negative 75 going to 25, that's 100 away from each other, 100 kilojoules away from each other. So 25 is not it, none of these are it. This is that because it's 100 kilojoules here, whereas this was 25 once we lowered it from 40. 23. What is the relationship between the equilibrium constant of a reaction and the rate constant for the forward reaction and the reverse reactions? This is kind of a visual I would memorize, which I did, and that is that Kc equals the equilibrium constant of the forward reaction over the equilibrium constant of the reverse reaction. So this is going to be our answer, and these are it except for B. If the half-life of a reaction is independent of the concentration, the reaction can be first order, second order, or zero order. So for our zero, this is also something you would want to memorize. For our zero order, concentration goes up. The half-life concentration also goes up. For our first order reaction, if the concentration goes up, our half-life does not do anything. It is completely independent. It will not change. For our second order, as the concentration goes up, the half-life goes down. It decreases. So second order is inverse. Zero order is directly proportional. First order is independent. They're independent of each other. So it should be first order as our answer. Okay, initial rate data for the reaction are given in the table. What is the rate law for this reaction? Okay, so we need to write out our rate law expression, which is K, concentration of A, concentration B. That's it. And so we divide. We need to take 2. We're taking 2 experiments from the table, and we're just plugging these numbers in. So for this particular table, our rate law is going to look like this. X, Cl2, concentration Y. So let's plug in some numbers. To find Y, we are going to want to find X values that cancel out. So these look like they would work well because 0.002 will cancel out, which makes solving for Y so simple. K's are going to cancel out. These are the same, cancel out, X's cancel out. 0.005 divided by 0.002 equals 2 to the power of Y equals 2.5 divided by 1.923. This is so simple because this is basically 2. This rounds to 2. So if we do all the math, we are just going to get 1. So we can stop there, and Y equals 1. I'll show you the math on when we're finding X. X, let's find a Y that would cancel, so we can use the middle 2. So we'll be using these. Whoops. Yes, okay. So same formula, except y, whoop, K, 0.0015. And I'm writing this out so that you can see the thought process. Also, if I come back to this video in a year's time or 2 and I completely forgot what I was doing, it'll be easier for me to follow. K's cancel, these are 1. And we can also stop here because if the rate if they are the same, it's going to equal 1. in solving this side, we are going to need to pull the natural log of both values. The natural log of 1 is 0, so, you know, our answer is going to be 0. I will write out the work, though, just in case people need a refresher. So 0.002 divided by 0.05, 1.333 power of y. Take the natural log to bring down that y, and the exponent yup. Yeah, and it's just gonna be 0. So why did I note that as y? This is x. So our x is gonna be 0. So if we do go to our, let's write it here. So x is 0, y equals 1. So let's just write what we got here. So h2 power of 0, because that is x. This is x and this is y. Cl2 is to the power of 1. The 0, h2 will not show up. So our rate law is actually just going to be KCl2. And the 1, we don't need to write it, that's implied. And this is our answer that matches. Oh, I didn't even circle. That is our answer. It matches up perfectly with what we got. The rate of conversion from cyclopropane to propane in the gas phase at constant temperature is a first order reaction. From the information in the graph, which statement about half-life of the conversion reaction is true? For this, we need to know that half-life, which is denoted as T sub 1/2, is the time it takes for half of something to decay. So I would just find a point on this graph. So 40 is pretty easy to see. 40 to 20 is a good 40. That's decreasing by half. And the time it takes from 40 to go to 20 would be our half-life. So the time in seconds at 40 millimeters of mercury looks to be about like 133 seconds. And for that to go to 20, it's 400. So 400 minus 133 is 267, which is very close to this answer. So this would be our correct choice. It took us around 270 seconds to have 40 decrease by half. Consider this reaction. If the rate of formation of N2 is 0.10 molarity over seconds, what is the corresponding rate of disappearance of O2? So O2, it's right here, our coefficient is 3. And what do we want? For N2, our coefficient is 2. So we can just do a fraction of 3 over 2 times our rate of formation. And this will give us 0.15 molarity over seconds. And that is going to be our answer, which is C. Quite simple. Which line segment represents the activation energy for the reaction between C and D to form A and B? So it's asking for this simple activation energy of the forward reaction, and that is it right here. This is the delta H of reaction, but this is our activation energy, so 3 to 4, D is our answer. The decomposition of hydrogen peroxide in the presence of iodide ion is believed to occur via this mechanism. In this mechanism, I minus is, so our answers are a catalyst, an activated complex, a reactant in the overall reaction, a product in the overall reaction. So we need to know that we need to know how to define a catalyst in a mechanism, which catalysts are used first, and produced later. Similarly, a good thing to touch on would be an intermediate, which is produced first and used later. So a catalyst, if we look at I minus, it is being used on the reactant side first over here, and then later it is being produced because it's on the product side. So this would actually be our answer because it matches perfectly with our definition of a catalyst. 30, which statement most accurately describes the behavior of a catalyst? Continuing on, a catalyst increases the delta G of reaction and hence the forward rate. Delta G is the change in standard, I can't spell in here, molar free energy. And that's not what a catalyst is dealing with. A catalyst reduces the delta H of reaction and hence the temperature needed to produce the products. So we showed here that this is the delta H of the reaction, and I mentioned that the catalyst lowers the activation energy. So that's this bump here, not this portion. So this is not correct. A catalyst reduces activation energy for a reaction and increases the rate of reaction. That is what a catalyst is the answer. A catalyst increases the equilibrium constant and final product concentrations. No, product doesn't deal with the concentrations.